Hello. In this video, I'm going to be showing you how to scale and modify existing sample structures so that your simulation matches experimentally obtained reflectivity data. In a previous video, you should have learned how to install my matrix toolbox and how to create sample files and also how to do some basic simulations on them. So in this video, we'll be fitting a sample and I'll also show you some data processing as well. So first off, as mentioned, you should have already installed the toolbox, so you can get to the demonstrations folder by going to Manage Add-ons and clicking Open Folder, and then we can go to Simulator Demo. And in here, there's a file called refl.mat. We're going to be working with that file, so I'm just going to go ahead and copy it, and I made this folder earlier, and I already put it in there. So let's go into that folder and work here. So the first thing we need to do is talk about what this file is. So I'm going to go ahead and open Quick Movie GUI so we can take a look at it. Load it into Quick Movie, and you can see we've got a series of images. And then we've actually run the reflectivity calculator algorithm from Data Analyzer to get the reflectivity out of it. And so now we have the unpolarized reflectivity image here. And you can see we don't have multiple images, it's just a single image for each field. And we can go ahead and hit the equalize button to make things apparent. And you can see we've got a pretty normal reflectivity here. Stop band in the middle, brag modes out on the edges, heavy absorption due to gallium or gas, aluminum gallium arsenide, 20% alloy, so that puts the band gaps or the absorption edge at like 680, 690 nanometers, and so you see everything below that is basically just absorbed. And so we're going to try to fit our simulation to some of this data. Now, this on its own, as we have it, is a lot of data. You know, we've got maybe hundreds of angles and hundreds of wavelengths. And so we want to sort of parse that down to a smaller subsection of that data, a little easier to fit. First thing we're going to do is trim this thing. So we'll trim the top left as about right about here, I'd say. And the bottom right as maybe, we don't need to go all the way out to 900, maybe just 850. And go ahead and hit that trim button. Okay. And now what we want to do is we want to recenter the vertical axis so that 0 is at the minimum of our parabolas here, or our brag modes. So let's see, it looks like we got to shift it up by about 2 degrees, so we use the shift button here. -2, I guess. Maybe 3. Yeah, that looks pretty good. And then we can go ahead and just put 1, 1, end, end. And now if I hit trim, it makes this 0 here, and now it's just automatically, so it's all set up and good to go. Okay, so now what we want to do is we want to pop out 3 of these types of figures for 3 different angles. At least I find 3 works pretty well, so we're going to do 3 here. But you might find that just using the normal incidence one is fine, or you might find that you want more. Depends what you're shooting for. By the way, you might be curious about these wiggles here. These are an artifact of the grading. So this data was taken in Bay 1 with a 50-line grading, and so there's interference fringes due to the grading. In theory, they should divide out when we calculate our reflectivity, but it doesn't always work that way in the real world. If you use a higher density grading, you think you might get rid of those fringes, but unfortunately that comes with the trade-off of having to use a stitching algorithm to put all the images together, and you end up getting a similar amount of wiggles anyways, so you might as well go with the thing that's faster for collecting data, the 50-line grading. So let's go ahead and pop out this 0 degree figure, and since this is experimental data, it's probably a good idea to average a little bit. So I'm going to tell it to average 5 pixels, plus or minus 5. Pop this out, and we'll go ahead and save this as refl 0. And then I'm going to try to get one at 15 degrees and one at 30. And the way I'm going to try to do that accurately is using a data tooltip. So this is the closest you're going to get to 15 degrees. So we go ahead and put our crosshair at this location. And now we can pop this figure out and save it as Refl 15. Now, if somebody from outside of our lab happens to be watching this video and using my software, first off, thank you. That's very exciting to know someone's using it. But second, you might have better reflectivity than us. This is sort of data that we had to take inside of a cryostat, and we don't have like a cryostat ellipsometer. This is just with freestanding optics. So you might have better data than this. All right, next up, oops, I was off by a pixel there. Next up, 30 degrees, Refl 30. Okay, so now we have all of our experimental data, and actually, let me look at something here. Okay, so right now we're getting a data point every 0.5 nanometers, which is pretty good. If we had, say, a data point every 0.01 nanometers, so like very high resolution, higher resolution than really is warranted for this type of procedure, I have an algorithm in here. You could have used smooth images horizontally, and then you could either tell it the exact grid you want, or you can just tell it to average to every 0.1. But in this case, it's already lower resolution than that, so I could maybe say every 1 nanometer. And you can see I downsampled it a little bit, but we don't need to do that because what we have is already a pretty reasonable data resolution. Okay, so now we've got our 3 figures here with our data. And we're going to go ahead and grab the microcavity sample that we designed last video from Dr. Pfeiffer's growth sheet here. Put that in here, and now let's go ahead and open up Reflectivity Gui. First, let's load the sample in, and next let's load the experimental data. So we'll start with Refl 0. You can see it puts it on here for us, and I'm going to click this Use Experimental Data button to just quickly take the range from this. And for now, I'm just going to delete those. Okay, and so you can see what we've got here simulated is far away from what we measured experimentally. And you can see that the experimental data is indicating that the sample is quite a bit thinner than we actually designed. That is typical of our samples. Usually it's like plus or minus a few percent. So this is nothing too surprising, especially because we have a wedge in our sample, we can move around, and so, you know, anywhere across the sample you might be able to drop from the design specs by like 15% at the edges. So let's just try scaling the entire sample's thickness. Let's try scaling it to 99%, see what happens. Okay, still too big. 98. 97's a little too little. So we start adding a little bit more back in, and now it's getting pretty close. And just looking at this, it looks to me like we maybe need to scale the experimental data up a little bit. If you've taken experimental reflectivity data with freestanding optics, you know it's very difficult to get your focal planes exactly aligned. And so it's not at all surprising to have a reflectivity that, you know, is a flat stop band, but it's measuring like 90% instead of 100%. All right, so now this looks pretty good, and we could start trying to tune some parameters to fit our simulation to this data. And the parameters of interest here are usually going to be the thickness of your DBR layers and the index of your DBR layers. Now, if I get a picture of my sample, I can see here that the DBR layers are gallium aluminum arsenide, or I should say AlGas, or aluminum arsenide. And then there's this small little wetting layer of gallium arsenide, but that's quite irrelevant for us, so we're probably not going to have to play with that at all. So we could go over here and create some variables for that. We can deal with aluminum arsenide, and Algas. And we can also change the index of them. Now, it's important to point out that the index of those materials, if you look at what we have here, it is actually wavelength dependent. So it is a little strange to tune it by just multiplying all of it by a constant, like 1.01. But that's a very simple way to do it. And so that's sort of what this is trying to do, is a simple reflectivity fitting. And then if you want to do more advanced fitting, you have to create specialized functions and use the material parameters table that I showed how to use in the last video. Now, right as we are here, we could try fitting this. But first, let's go ahead and try tuning these. All right, so we're going to let us tune the real index, the real part of the index of aluminum arsenide, the real part of the index of Algas. And in general, the imaginary parts of these things aren't really all that big. So you see, yeah, this is like 10 to the negative fourth for Algas, and aluminum arsenide drops off very heavily at wavelengths lower than what we already have. So we probably don't need to really touch the imaginary piece. So what I'm going to do is I'm going to do a one-shot optimization. So before I do that, I'm going to make sure to save my GUI state. And I'll put this as one figure start, because eventually we're going to be fitting all three angles simultaneously. And now if the fitting algorithm gives me some silly nonsense, we can just click on this file here and get back to where we started. Okay, so now what we want to do, we're going to make sure infinite tune is turned off. So this is just going to be a one-shot optimization. And we go ahead and click Optimize Reflectivity. And it's asking you, do you want to work with reflectivity or maybe an integrated field like the energy dissipation if you're trying to fit PL data or absorption data, things like that. We're going to work with reflectivity fields. And what variables are we allowed to tune? So the total thickness of the sample, this 0.972. The scale factors of the aluminum arsenide and the Algas, that's basically just saying, all right, maybe the machine that grew this were all systematically off by, plus minus 1% or something like that. And then we can also scale the index of those two materials. Now, this is actually too many unknowns for what we're trying to fit, because well, it's just too many. But when we have three angles all at the same time that we're going to be fitting, then all of a sudden it's more well constrained. And then you could also choose to let it shift and scale the experimental data to get even better fits. With reflectivity, that's probably not too important. For fitting PL, that can be very important, but reflectivity is always sort of, it's going from 0 to 1. It doesn't change. We could play with temperature, but I don't think we want to do that. And we can play with angle, but we know this is at 0. Okay, so we hit OK. And now it's working. And if you go and look at the terminal, it tells you how many evaluations so far. So it's done 50 evaluations so far. Now it's done 100. And my guess would be that this will come to a conclusion by 1,000 evaluations, but I'm not going to make you watch that, so I'll go ahead and stop the recording here, and I'll come back when the fitting is done. All right, I'm back. I shouldn't have bothered to turn off the recorder because it only ended up going to 240 evaluations before it decided it was at a local minimum. But just looking at this, it does look to me like it's already, a bit better. So let's go ahead and pop this out, and then let's open up what we started with. Pop this one out. Let's compare them. Well, maybe not much better. Okay. Now, in order to get really good convergence with this type of thing, if you really want your experimental data to line up very well with your simulation, what you want to do is enable infinite tune. And what that will do is every time it settles down and concludes that it's at like a local minimum, it'll randomly change all the tuning variables by plus or minus 1 point, in this case 0.02%, or sorry, 1.0002, so plus or minus that range. And then it'll re-optimize them. And so it's sort of like a pseudo randomized function optimizer. And if you let that run for 8 hours overnight while you're asleep, maybe it'll do like 50 runs total, and then when you wake up, you want it to stop optimizing, so you go ahead and turn off infinite tune, and once it finishes the current algorithm, it'll take the best out of those 50 runs. It'll put the values into the GUI window, and then it'll run the simulation one more time just to show you the best fit, and it'll be done. So, but we don't necessarily want to do that right now, because actually we want to go ahead and set this up for three three angles of fitting at the same time. So first thing I'm going to do is I'm actually going to dock the Reflectivity Gui, and then I'm going to pop it out like this, and that's going to help us out because we're going to have 3 of these windows. So now we're going to go ahead and click the Chain GUI button, and we're going to dock this. And now what we want to do is load experimental data into this one. And now if I hit update reflectivity, it updated both GUIs. And we can see how the data compared. Oh, and I forgot to put 15 degrees here. That's why it's quite a bit off. So now if I hit update, now I see, oh, it lines up fairly well at 15 degrees. This isn't ever going to look perfect because there's a lot going on. When you have hundreds and hundreds of layers growing on top of each other, you've got all sorts of strain effects and just impurities sometimes. Even though these samples that Dr. Pfeiffer or Dr. Wasilewski grow are very pure, it still is an issue. And yeah, so this looks pretty good. If we had, say, different polarizations, we could enable that in here. If we had different temperatures, if we were fitting at multiple temperatures, we could try that. But we don't. So now we're going to go ahead and open up a third one. And we're going to load in the 30 degrees. Hit the update. Okay, and this one's a little bit more off, and usually you're going to find that at higher angles it has a little more trouble. Now, also, this data we took was unpolarized, and since there is TETM splitting, now that we're going out to finite angle, not just 0, we need to actually say that we're using unpolarized reflectivity. And so we'll go ahead and set that for all 3 of the GUIs. Okay, unpolarized, unpolarized, unpolarized. Good. And looking at this, we might be ready to do another optimization, I think. Yes, I think so. So once again, this time I'm going to set infinite tune. I'm going to let this go for maybe, I don't know, maybe 30 minutes, just see how good it can get. And so I'll tell it, all right, optimize my reflectivity. We're working with reflectivity. And we're going to use total thickness, thickness of the layers, real index of the layers, and that's everything. So those are the variables it's allowed to play with. Hit OK, and let it go to work. Now, of course, this is going to be a little bit slower because now we're doing 3 GUIs at a time instead of just 1. Well, actually, now that I think about it, I could just dock all of this. And then, yeah, once it has the next update, the next draw update, we'll get to see this GUI correctly. Okay, looks a little bit squished, but we can cycle through and look at how the fits are going. All right, I'm going to let this run for maybe 30 minutes, and then I'll come back. So I'm going to... Okay, we're back. I ended up letting it go for about 2.5 hours, I think. Okay, good. So it just finished up one randomization, and you can see that it tells you the parameters order, the best parameters so far, and how it's randomized them to then begin trying to fit it. And now I'm going to say, okay, well, it's done 35,000 evaluations of the function. That's enough. So I go ahead and hit infinite tune. So now I've turned off the randomizing, and now it's going to finish up its current evaluation. And then when it's done, it'll show us the best possible fits that it's found. So I don't want to stop the video because I want you to be able to see it happen live. But hopefully it'll only take a minute at most here, I think. It's certainly getting close. I suppose on YouTube you can just speed ahead a little bit here. There we go. All right, so that was the 114th randomization. That's how many evaluations, and now it's put the optimal parameters into our GUI. So let's take a look at the fits. So yeah, things are mostly lining up. Peaks are lining up with peaks. Minimums are lining up with minimums. Let's see, in 15 degrees, still lining up pretty well, so that means we've got the curvature. Yeah, lines up pretty well out at 30 degrees too. So we've got the curvature pretty well. Now, I know this isn't the best looking fits, but my argument to you is that it doesn't matter so much, because what we're really going to be interested in is these two dips, which are the polaritons here in the middle. And as long as we have a stop band reasonably close to what we want, I'm going to say that this sort of all acts as background noise. And I've done some simulations, you know, where I sort of screw up the parameters, and I show it doesn't really influence the polaritons all that much. So with this all done, we can go ahead and close the higher degrees GUIs. Now we're just at normal incidence. And now if I hit update, you'll see it doesn't do anything with the other GUIs because they're gone. And now what we want to do is probably save this. Now again, you could save the scaled sample, but then these values, you can't change them if you need to. So what I like to do instead is actually save the state of the GUI. So I'll go ahead and save this as fitted P6 1919. And because you can see we had P6 1919, now we fit it. And now that's it for this video. So now I've shown you how to get reflectivity from your 2D image, fit it, and let it optimize for a bit. Next up, we'll show you what to do with this in the next video.